your review sheet for the test tomorrow. In front of you here you have all of the definitions and all the words. That is the correct way to spell them. Everything is right here. Everything that you see right here is something that you just need to put some time in, get it done, figure it out. So if you need to pause here and do whatever you do, pause it here and get all this written down and ready to go. But all this stuff needs to be known. Should all be stuff that you are able to handle. Fill in the blank wise, you should know it that well. Moving on. Another thing I told you we needed to learn was how to do this, and excuse me, you will have a diagram similar to this, and where you'll have two different substances. At the top here we have water, underneath that we have glass. When the water ray comes in, it comes in at a 30-degree angle, and it's going to bounce out, and some of it's going to refract in. So to fill in the blue here, the first angle, the angle coming in, is called the angle of incidence. And so that's the incoming angle. And then when it bounces, some of the energy is going to bounce, and bounce is reflected. So this is the angle of reflection. And then down at the bottom, it's going to bend because we're entering a new medium. We're going from water into glass. So at that point, we are refracting. So that's the angle of refraction. So you'll need to know those three words. You'll need to be able to spell those three words, hopefully better than I do. And then we need to fill in some numbers. Well, up at the top, this red angle here, the angle of reflection, if it comes in at 30, it's going to bounce out at 30. So that's really tough math. So everybody should be able to handle that, no problem. How do we get the angle of refraction, the green one? Well, to do that, we need to use Snell's rule. N1 sine theta 1 equals N2 sine theta 2. So when we look here, we have the N of water goes with the angle up here in the water. So we're going to have 1.33 times the sine of 30 equals, well, what is the other n? The other n is 1.52. So we're going to have 1.52 times the sine of x. We put x in there because I don't know what the angle is down there. So that's our x. So if I'm looking for this, first I want to get this by itself. So I'm going to move the 1.52 underneath here. So that would give me this. So after plugging in that, we end up with 0.4375 equals the sine of x. Well, I don't want the sine of x, I just want x. So I have to unsign this. So I'm going to hit second sine, and then in the parentheses, I'm going to stick that number, or I can hit second answer if I don't like to retype again, which I don't. So second sine, second answer. And that gives me 26 degrees. So down here, this would be 26 degrees is what goes right in there. And that's how you find those answers. Moving on to the next one. In question number 4, this is very similar to what we just did. It says light falls in a clear pool of water at an angle of 59.4 degrees measured from the normal, of course. Some of the angle is some of the light is reflected, most of it is refracted into the water. At what angle is the light reflected? If it comes in at 59.4, it goes out at 59.4. So again, angle in equals angle out. So that's all we have to do for part A. Really super duper simple. When we get to part B, we're asking at what angle is light refracted? And again, for this one, we're going to use Snell's rule. So N1 sine theta 1 equals N2 sine theta 2. So the N1, we're in a pool of water. It looks like it's in air before it hits the water. What do you know? So air is 1.00, and the angle in the air was the 59.4. So again, we want to look and say, in the air, it was going 59.4. What is it when it refracts into the water? So inside the water, we're at 1.33 times, again, the sine of x. So if I want to find first the parentheses here, I need to move the 1.33 underneath. And so that's going to tell me that the sine of x is equal to 0.647. So to find x, I need to unsign that. So second sign, second answer. Second sign, second answer. Of course, we always have to be in degrees when we're using sign. We end up with 40 degrees here. So that's going to be 40 degrees. Excuse me. And so that's what we got to do for part B. So easy. Going on to number 5. We have a convex lens with an 18.8 centimeter focal length. So 18.8 centimeters is our focal length. That's going to be the F. That is placed 19 centimeters away, 19.0 centimeters away from the candle flame. Well, the candle flame is our object, so this is how far the object is. So that's the DO distance to the object. The object is 8.2 centimeters tall, so 8.2 centimeters is the height of the object, so that's our HO. And again, all three of these turned out to be in centimeters, so we don't have to convert anything, so that's cool. And it says it projects a perfectly focused image on a wall nearby. Well, if it forms an image on the wall and I ask how far away is the wall, really I'm asking is how far away did the image form, because the image forms on the wall. So I'm looking for what is DI. Well, again, if I remember that 1 over F is 1 over dou plus 1 over di. If I look at here, dou and di are connected with a plus. The opposite of plus is minus. So I'm going to have 1 over F minus 1 over dou equals 1 over di. So again, we're going to look for that little magic x to the minus 1 button on our calculator. If you start at the number 7 and you go up 2 and to the left 1, it's right there. So all we have to do is push that 3 times because there are 3 different numbers here. So the F number, we're going to have 18.8, and then we hit x to the minus 1, and then we're going to subtract the dou, 19.0, x to the minus 1, then we hit equals, then we have to hit x to the minus 1 1/3 time so that we flip our answer and hit equals again. And that gives us a grand total of 1786, which of course we're going to round to 1790 centimeters. And if you don't like the way that number looks because it's centimeters, you can always change it to meters if you want. So that would be 17.9 meters if meters make you happier. If you want to leave it in centimeters, that's perfectly fine too. So that's it for part A. In part B, it asks, how big does the candle flame look on the wall? Well, how big does the candle flame look? That's going to be the high. High is only found in high over HO equals di over dou. So if we start off with this, again, if we're looking for high, HO just needs to move up, and we end up with HO d over dou. And so the HO was, how big is it? Well, a minute ago we said that the HO was 8.2. So that's still going to be 8.2. And then we calculated just a little bit ago that our distance to the image was 1790. So 1790. And then we divide that by our dou, which a minute ago we identified as 19. So that would be 19.0. And that, after rounding, will give me 770 centimeters. Or again, if you prefer it, you can put it in meters. So we would have a very, 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 very big candle flame on the wall, 7 meters tall. That would be pretty huge. And again, you can easily just leave this in centimeters, and that's a perfectly fine answer also. When we get to point C here, C is asking, what is the orientation of the flame's image? Well, the flame was a real image because it was focused on a wall. If we know it's focused on a wall, we know it's a real image, and we know that real images are always inverted. As we saw in today's lab, every time we had the thing that actually formed on the piece of paper, the flame looked like it was pointing down instead of pointing up. So that should be easy. In part D, we asked, is this a converging or a diverging lens? Well, again, we formed a real image, and when we were making our little ray diagrams, what we noticed that the real images only happen when the light rays cross. And so if the light rays cross, that's only because light rays are coming together. Light rays only come together when we have converging lens. So a converging lens can make a real image. A real image cannot be made with a diverging image. So if we have a real image, then we're going to have a converging lens. So that's going to be easy. The last part was an example of transparent, translucent, and opaque. And again, a transparent object is something you can see through very, very clearly. So soda pop glass, or regular water, clean water, or just clean glass off a window. Those are all good examples of transparent. Translucent would be something that you can see through, but it gets distorted. So that could be like skin or shower glass or white milk jug plastic. And opaque objects are objects you can't see through. That would be brick wall, wood, exciting things like that. The last thing that I told you is going to be on the test is you're again are going to have to draw a ray diagram. So again, if we have a ray diagram, we're going to have an F on both sides, and we're going to have twice that, and it's going to be 2F, and so we should have some sort of object, usually like an arrow or something exciting. And again, the lines you want to draw is anything that comes in parallel to the principal axis there is going to get bent through F. And anything that goes through F on the way to the lens will get refracted out parallel to the principal axis. Since it crosses with the real image, that's going to be where the top of the arrow forms. The top of the arrow used to be up here. Now the top of the arrow is down here. It's inverted. It's smaller. That's all you have to do. So you're going to get points for making sure that the bending actually occurs at the lens. The bending doesn't occur at some random point in midair. And that we have nice straight lines that are actually going through our focal points, both a focal point here and a focal point there. And you'll have little rulers to work with so you can be all nice and neat. And that's it. You guys should dominate. There should be no excuse for anybody not getting Smarties. A great opportunity, again, to raise a grade before the final exam.